So here in part 2, this is where the Frenet-Serret kind of stuff is going to come into play. So right here I've pasted in as a comment some differentials that I'll just read it out. So on the left hand side you can see this is some differential radius with respect to arc length. And then on the right hand you have the radius with respect to time, and the denominator the arc length with respect to time. So going off of this, this is where we're going to use a function to kind of find these vectors, a tangent and normal vector, and we'll use those to eventually get to plotting like our curve, or our surface onto our curve. So looking at this, really the first thing we need to do is get our function kicked off. So we can call this friend. Let's do the first name, and then we should supply that with some function. And since we're using f, this is kind of what we're going to go by. Instead of r, we'll do df, and then df dt over ds dt. Okay. Oops. Okay, so characterizing this df dt. Well, when we supply our function, that will, it'll be very easy for us. We can just take the Jacobian. It should be Jacobian of this function, and so we're going to be able to use this when calculating our tangent curve. So this is where we can make our next function, this higher order function. So define tangent. The tangent vector, a given tangent vector will depend on time, right? Its location on that curve will depend on time, where that tangent vector is. And we're going to use this same thing to determine the tangent vector. So in order to do that, it should be our df dt, right, at some given time, as we defined here, right? And that divided by ds dt, right? If you divided these, the dt's would cancel, so you could just write it as ds over, well, how do we want to name that, I guess, then? Because it's something that we don't know. Oh, yeah, we do. I didn't name this right. Sorry, I meant to say that. So it should be ds dt. ds dt. No, sorry, I'm getting mixed up. That should be df dt. Since we don't know ds dt, I think we're going to have to create another function to be able to find that. So let's call this one ds dt then, right? And that would be very similar for a given t. So how can we get this? With what we know, we could find the norm, the vector norm of df dt. So let's see if I can remember this. Jax has something already built in here. So ln alg dot, maybe it's just norm. That's right, probably. Yep. So then we want to supply that df dt as a function of t. Okay. This function needs to return that. Okay, now we can come here and we have our ds dt built in. define that up here. And this needs to also return. Okay, so now we have our tangent function. Now, this d-tangent, in order to find our normal vector here, we're going to need like a differential tangent. So like d-tan, how about d-tan dt? And this will be easy to get using our Jacobian once again. Instead, this time, we'll be finding the Jacobian of our tangent function. So Jax dot Jacobian of tangent. So once we have this, we can find our normal vector. Oops. So we can just call this one normal, again for t. And this time, so when we're using this, from this we can get our normal vector. Oh, I'm sorry. Yeah, this is another thing that's important to point out, really. What we're interested in is the unit vector for the tangent and normal vectors. That was part of why we just kept that as is. And when we're using this tan dt, we're going to need to divide by the magnitude of the vector by using that Lin algebra to normalize the vector and get that. So let's just call this like vec, store a vector in there, and then we'll use our d tan dt evaluated at t, and here's where we'll just divide by the ds dt again, right? So now we have this vec, but we need to have the unit vector. So we're going to take vec and divide it by jnp, right? jnp dot lin alg dot norm of vec, right? So that will give us our normal unit vector, and so we want to return our normal and tangent vector. That's what we're interested in. So we'll do tangent and normal. See if that works. Okay, that looks like that's all right. So let's see what happens if we store those into a variable, right, using our curve. So given that this function returns tangent and normal, we can store those, those exact return values into their own respective variables. So then we'll use our Frenet function using, again, the curve similarly to up here, where we'll supply our curve to the function. So there's our f, and then we want to return our curve with only respect to t. Supply these. Okay, so those are stored in there now. So if we just hit tangent, we should see our functions. Yep. So that's stored as that. Oops. Let's see, normal. Should both be good. Okay. All right. So then the next thing we're going to be able to do with these unit vectors is we'll characterize the surface of our kind of tube shape. So we'll get onto that.